Okay, this is 15.3, number 8. This one is a centroid problem, so again, it has no density. The density is 1, but the bounding area is pretty complex. We're in the first quadrant, the y-axis, and then these two parabolas. And so let's organize ourselves and see what this guy really looks like. So we've got our first quadrant, and the y-axis is one of the bounds. And then we've got these two parabolas. Let me rewrite them. This one's going to be y equals 1/8 x plus x squared plus 4. And this one's going to be y equals 1/4 x squared. So this one is above because it starts, when x is 0, it starts at 2. No, 1/2. So we're up here at 1/2. So I think that's the upper one. Yeah, because this one starts at 0. So let's draw the lower one in first. It does this. And then this one is flatter, but it starts at 1/2. So it does this. And what we're interested in, of course, is finding that intersection there, because that's what's going to make this an area. And this is the area we're looking for. So it's bounded by the y-axis, it's in the first quadrant, and then these two parabolas. So let's see what that intersection is first. So let's set these equal to each other. So we got 1/4 of x squared is equal to 1/8 of x squared plus 1/2. So taking this away, 1/8 away from 1/4 is 1/8. So we'll have 1/8 x squared equals 1/2. Or multiplying both sides by 8, we'll have x squared equals 4, or x equals plus or minus 2. Well, clearly it's only the plus version. If we drew these across, they'd also intersect over here, but we're only interested in the first quadrant one. So this is 2. We can also find its y-coordinate, because we're eventually going to need that. And of course, the y-coordinate's going to be, if I plug 2 in for x, that's 1. So this is 1. That's 2. This is 1/2. Okay, so at least we've got our area now kind of outlined, and now I can go ahead and draw in the vertical pieces, and then I can see what I have to integrate in order to find the mass. So the mass is going to be the integral in the x direction at 0 to 2. In the y direction, it's the difference in the height, so it's going to be the integral between the upper minus the lower, and the upper one is the 1/8 of x squared plus 4, and the lower one is 1/4 x squared. And then what are we integrating? Well, for the mass, we're just integrating the density, which is 1, so it's dy dx. And I've already worked this one out. You have to take the y integral, plug in these limits, and then take the x integral and plug in these limits. When you're done with the whole thing, you get 2/3. And then the mx, let's do the my because it's already in this configuration. So my, and that one's going to be the same integral, 0 to 2, integral from 1/4 x squared to 1/8 x squared plus 4. But now it's got an extra x in it, so this is going to be x dy dx. And then that, when you go through all that work, is 4/15. And then finally, we've got the my, or mx. And mx will insert an extra y, and then it's over the same limit. So it's the integral from 0 to 2, and the integral from 1/4 x squared to 1/8 x squared plus 4, and it's y dy dx. And that one equals 1/2. I think I got these reversed. That's what happened. This one's 1/2. And this one is 4/15. There we go. So now we can find our center of masses. So in the x direction, our x center of mass is my over m, and of course, that is equal to 1/2 over 2/3, which is 3/4. And our y center of mass is mx over m, and that's 4/15 divided by 2/3, and that's 5 and 2. It's going to be 4/15 times 3/2, and that's 2/5. So that's the x center of mass and the y center of mass. You might wonder, why didn't we turn it sideways so that we could integrate the y in terms of those pieces up and down? And the nice thing is, with two-dimensional integrals, we don't have to do that. We can do the same two-dimensional integral all the way along. The thing that makes it orient around the x and y axis is the fact that we multiply in by an extra y or an extra x. So unlike the single dimensional, where we had to turn our little differential piece, you don't have to do that with the 2D ones. You can integrate along the piece where the height difference in the y is simply provided by the limits of integration. And it's this function here that takes care of the fact that we're measuring it either up and down or left and right.